Hi, everybody. I'm Michael Lazos. I'm a software engineer at Meta. And today, Henry and I will be presenting our work generating state-of-the-art GEMMs with TorchInductor. This work is a collaboration between others at Meta as well. Ruben contributed the Composable Kernel backend, and Driss contributed the CuteDSL backend. And so now I'll quickly just go over the agenda. First, I'll cover the motivation, the current state, and why we use vendor-specific libraries to optimize GEMMs. And then Henry will cover our integration into PT2 with the CUTLASS and CK backends. Then it'll come back to me where I'll talk about how we further customize CUTLASS kernels with Epilogue Fusion, and then how we utilize that Epilogue Fusion to accelerate float-8 GEMMs. And then we'll close out with the ongoing work, which is to integrate the CuteDSL backend. So first, I'll cover some background. This is how GEMMs were handled in TorchInductor before our work. And so without autotuning enabled, TorchInductor will just scan your model and find all of the mapmul calls and convert them to A10 calls. This will just dispatch to cublas for Nvidia and HIPBLAS for AMD. The main disadvantage of this approach is that it doesn't allow fusion. And so we can't, and this is due to our inability to fuse with compiled binaries. To get around this, we use Triton, which we can fuse with because TorchInductor generates pointwise ops using Triton. But in order to get comparable mapmul performance to cublas or HIPBLAS, we have to autotune. And so the reason autotuning is necessary is because in the past decade plus, GPU architectures have become really complex with the rise of deep learning and AI use cases. In order to handle a large variety of workloads, new hardware features have been added, and this increases the architectural complexity. And as a result, there's really like a ton of different choices you can make when you're designing a GEMM kernel. A small subset of these choices are the tile sizes, whether you want to use warp specialization, what kind of instruction shapes you want to use. For some workloads, small instruction shapes will be better, and for others, larger will be better. And then also whether you want to use asynchronous memory transfers, and these are known as the Tensor Memory Accelerator on the latest GPUs, Hopper and Blackwell. So the simplest auto-tuning solution to the problem of too many choices is just to try them all. And sometimes there are way too many choices, and it'll actually take forever to try them all. You can auto-tune for days and days and get all of the optimal GEMM kernels in your model. And so to get around this, a lot of libraries will configure user-tunable knobs, which will allow you to tweak the search space, or also introduce heuristics, which can also make the search space smaller. And so in order to reach SOTA performance on GEMMs, we opted to use both AMD's Composable Kernel and Nvidia's CUTLASS library. These both support autotuning as a first-class use case, and our belief was that a compiler should be able to optimize choice as well, given a specific problem. As a JIT compiler, you have the information at runtime on what problem sizes you're going to be tackling, so you should be able to make the optimal choices. And so one note I want to make here, though, is our goal is not to beat cublas on all shapes. Cublas and HIPBLAS are both heuristic-based approaches which can't have full coverage in all shapes. Your binary size would get too large. And so in order to get full coverage on all shapes, that's where our auto-tuning approach would come in, where we can then see these shapes that aren't well covered by cublas and HIPBLAS and optimize well for them. And this also has the advantage that it allows flexibility for fusions, and we won't be dependent on Triton performance optimizations on new hardware. The latest an example of this is with warp specialization. Triton just recently added this when other vendor-specific libraries had them earlier when the newer hardware was released. And so this drives home the point that vendor-specific libraries tend to be lower level, and this really just follows an industry trend that in order to utilize the architectural advantages of each vendor, you need to expose those capabilities to the language you're using. And to drive this point home further, our own Ed Yang declared Triton dead due to its lack of Blackwell performance. But I don't necessarily subscribe to this, but I think that Triton's lack of Blackwell performance is leaving an opening for these lower level libraries to perform well and threaten its dominance from the past few years. And so with that, I'll hand over to Henry, who will cover our integration with TorchInductor.
Hello, so I'm Henry, software engineer at Meta. So how are we going to use the gems generated by CuTLASS, CK, etc.? It's kind of, we have to deal with the templates ourselves, we have to compile it, and then we have to pipeline it, etc. We want to provide a easy-to-use solution through TorchInductor. Basically, we want it to be hardware agnostic on the TorchInductor level. Basically, you use torch.compile, turn on a flag, and you'll be able to use gems generated by CuTLASS and CK. And especially crucial is that we are able to, through TorchInductor, we use some components that we already have for Triton backend. Let's take a step back and talk about how we do it for Triton currency. How do we generate a gem with Triton, or how does Inductor generate a gem these days? The way it works is we have a problem shape, which is like M and K for gem, metmo. We have a torch the metadata we need. We have data type, we have layout. And then inside TorchInductor, we are going to generate one choice with cublas or HIPLAS, depending on the hardware. We are going to generate multiple choices using templating for Triton. And then we're going to use Triton compiler to compile them just in time, parallel. And then we're going to benchmark all the choices we have to see which one is the fastest for our specific shape and data type, layout, etc. So in other words, if we follow this pattern, all we need to do is, well, instead of generating, alongside with generating templates for Triton, we just generate C++ code for CuTLASS and CK. Instead of compiling with Triton compiler, we just in time parallel compile them with MVCC or Tsang, depending on which backend we are using. After that, we have a dozen choices. We're just going to benchmark them and figure out what is the best gem to use in our problem shape. So here's the auto-tuning workflow. I'm not going to talk about the picture on the right-hand side. It's just templating, compiling, and auto-tuning. I just want to highlight one advantage of this method. The idea is that we don't have to think about it too much. We can just look at any combination of configs. We pass them into the templates. It's going to generate C++ code. And then we are trying to compile it and trying to run it. Well, we don't guarantee that all of them is going to run or compile perfectly, but as long as we catch it, from the user point of view is that you pass in the metadata and we give you a really nice gem to use. So what do we support? By default, we support torch.compile, basically the recommended entry point for Python usage to compile a model. We also support AOTI, which is like the twin brother of torch.compile for serving a model in C++ runtime. We support dynamic shapes. Again, we try to mimic the support we have for Triton. In particular, I want to highlight our innovation for dynamic shape, namely, when we do templating, we make the gems input shape agnostic. So you would generate one kernel, one C++ code, compile it into one .so, and it will be able to handle basically all the shapes that you pass in. We will still auto-tune on one shape, but that kernel has the capability of serving multiple shapes. We also support various kinds of caching to make sure the integration is nice and easy to use. Again, we made the templated gems input shape agnostic so that they are highly reusable. For different shapes, you can just reuse the same .so artifacts. And this is like a mitigation to CuTLASS long compilation time, which we might come back when we talk about CuteDSL. So what are the results? On H100 with the CuTLASS backend, we see decent performance compared to AOTIn and slightly outperform Triton. And I just want to reiterate the motivation we talked about at the beginning. We don't aim to beat AOTIn on all the shapes. What we care about is full coverage of shapes through auto-tuning and flexibility for fusion. And another thing I want to note is that results depend a bit on CUDA version because cublas, aka AOTIn, improved a bit since CUDA 12.6. And similarly, we have results for CK backend. What we are seeing here is a varying, like a mixture of results, as in on some shapes, Triton is performing better, on some shapes, CuteLASS is performing better, which is actually what we want to see. We don't want to see one backend performing the best on all the shapes. That would kind of make other backend less useful. And then we tested the shapes, all the graphs, we tested them on Llama shapes. So we didn't capture all the shapes, but from experiments, we see better performance on some non-standard shapes, like split case shapes, etc. So I'll hand back to Michael to talk about Epilogue Fusion for CuTLASS.
So now I'll talk about how we further customized CuTLASS kernels with Epilogue Fusion. And so in ML models, typically GEMMs are followed by an activation or some point-wise ops. They can also be followed by reductions, but the main point is that they're followed by some memory-bound op where the GEMM compute will dominate the memory reads of the Epilogue op. And so the main goal of this fusion is to hide that memory read by applying those ops directly to the elements of the result of the matmul as they're computed. And this also removes the memory transaction that would typically happen after the matmul. So here in this diagram, you can see in the typical case after a matmul, you'd write back to the result to global memory, and then the activation function or Epilogue pointwise op would read that result back, and that adds latency. And so we can remove that memory transaction and just append those ops directly to the matmul kernel. And so initially, we tried to generate C++ directly, and this didn't really work out well. It's really complicated to emit CuTLASS C++, and I would not want anybody really to do that after our experience. But the performance was really good, so directionally, this was the right thing to do, but the maintenance burden from the compiler complexity was too high. And so we deprioritized this work until new features of CuTLASS allowed us to implement this a lot more flexibly. So some of the features that CuTLASS added were the Epilogue visitor tree API and a Python tracer. This allows us to drastically reduce the complexity of the compiler while generating the C++. And so what Epilogue visitor trees are they're a composable CUDA kernel library. They're built out from these templatized kernel classes, which are really similar to the GEMM universal templates that CuTLASS already provides. And so they provide the extensibility to basically change all of the different kernel metaparameters via template types on the class itself. And so this allows you to auto-tune the Epilogue similarly to the way you'd auto-tune the GEMM. And so this is all open source, so it was really easy to see the code and extend it if we needed to. And then additionally, in addition to that API, the Epilogue visitor tree API, CuTLASS also provided a Python tracer to generate the C++ templates. TorchInductor is already good at generating Python because we generate the Triton ops, and so this was an easy extension compared to generating C++. And so here's an example of what an Epilogue visitor tree will look like. It represents the expression on the left as an abstract syntax tree of ops on the right. And so this allows you to compose an arbitrary sequence of ops in the Epilogue right after the matmul and allows you to do it easily in that it will all, as you add more ops to the Epilogue, you can just treat it as any other Epilogue. It's all, it's composable in that way. And so here's actually what the Epilogue code looks like that Inductor generates. And so you're allowed to use a subset of Python where all of the ops in your expressions are supported by CuTLASS, and all variables need to be assigned once. And the way this Python tracer works is it goes through this Python function. It generates an expression tree from the Python expressions using Python's introspection APIs. And then, as you can imagine from there, it basically visits that expression tree and generates the Epilogue visitor tree from that expression tree. And so in order for Inductor to generate the Python code, we have what we call an ops handler. And so TorchInductor is defined by run_ir, uses this technique to, in the IR on the left, you can see that we have ops.mul and ops.relu. The ops handler itself is overridable. So you can basically override ops to mean anything you want. A lot of our analysis passes are implemented with this technique where you can analyze memory usage, you can analyze shapes, and this allows us to basically implement different operations over inductor's IR. So in our case, when we want to emit Python code, we just make a Python printer ops implementation so that ops.relu will just print the code on the right, the relu cum expression there, and then ops.mul will just implement an inline multiplication on the right. And so this allows us to translate arbitrary expressions to Python code. And so in order to integrate with the Nvidia EVT tracer, you have to pass it some metadata through this API where you define a dictionary where you map each name used in the example Epilogue to a fake tensor. And so these fake tensors are distinct from the PyTorch fake tensors in that they just basically encapsulate some metadata that the tracer will need to generate the correct CUTLASS code. And so some of this metadata is just the data types, so it can know when to do type conversions in the Epilogue visitor, and then the shape, so it can do shape analysis and add reshape operations, and also the layout in order to also analyze the reshape operations. And so once you pass in this dictionary, you can just trace that Python code and get the C++ code that you want. And so here's an example of the generated C++. You can see how it's implemented types for each of the different pieces of the tree. So a cum here is loading the output of the matmul. Alpha is the scalar that I showed before. It's doing a scalar broadcast, and the same thing with beta. And then compute 0 is saying we're going to do a multiply. And then this is an actual node in the tree where it's applying the multiply to the alpha and the accumulator. And then similarly down here, it's also applying a multiply to the beta and tensor C. And this isn't the whole code because it's actually too big to fit on the slide, but as you can imagine, you wouldn't want to really write all this by hand as the tree it's pretty large. And so in essence, you're embedding the tree structure in the C++ type system. And so overall, here's the whole system of the phases I've described so far. You have the model, which torch.compile will then generate the inductor IR. And then from the inductor IR, we go to the Python EVT. And then from there, we trace that Python EVT into the C++ EVT. And then we splice that code together with what the system Henry described. We get the regular C++ GEMM, and we generate the compiled SO from both of those C++ snippets. And so here are performance results for a ReLU add benchmark with bflow 16. It had a 6% geomean speedup on the shapes used in Llama, and a 6% speedup versus Triton, and an 8% speedup versus A10. And you can see the difference between the max speedup and the geomean speedup really shows you that there are some problems where this auto-tuning technique is really applicable, and then other problems where it might not give you as much benefit. And so the max speedups are pretty good. On some problems, we're getting 50% to 60% speedups over Triton and A10, respectively. And so here's a more in-depth analysis of the results. On the left, we have m equals 64, and on the right, we have m equals 65,536. And on the x-axis here, we have all of the shapes from Llama. And so when we did the geomean, we had m range from those two values, from 64 to 65,000. But you can see that CUTLASS usually outperforms Triton, and definitely both Triton and CUTLASS outperform A10 because A10 isn't doing any fusions. And so there are still some shapes, where Triton also outperforms, as Henry mentioned, where we're not really aiming to win on all shapes, but on a lot of shapes, CUTLASS is definitely providing a performance boost. And so we used the Epilogue visitor tree technique not just for arbitrary epilogues, but in this case also for when we know the epilogue in advance. So for float8 GEMMs, you often scale the output either row-wise or tensor-wise. And I have the example epilogue for that on the right here, where you just, to bring the value back to bfloat 16, you have to scale it. And you also can optionally add a bias. And so we wanted to use Epilogue visitor trees for this because instead of hard coding, you might have to hard code every option where you might want to add the bias or allow additional fusions. But using the Epilogue visitor tree API allows us to leave those doors open for the future to have even more flexibility. And so here's how you would use the FP8 gem in your model. You would get the X and WT matrices from the quantization beforehand, where you'd quantize those values to FP8. And then you'd get the X inverse and W inverse scale matrices from that quantization as well. And then you can also specify whether you want to use fast accumulation. That uses a technique in Nvidia GPUs where it will use the tensor core accumulators, which will periodically sync back to registers to upcast. But this is basically an accuracy versus speed trade-off. And typically, it's true for inference, but false for training, because the accuracy loss will mess up training often. And so here's the C++ code for an FP8 epilogue. It's really similar to what we showed before. And you can see that we do a column and row broadcast. And then we do a multiply again with the accumulator. We just do 2 multiplies. And that was the epilogue I showed before. And so here are the performance results for FP8. So here I show both all the backends with the fast version, which use fast accum, and then all the backends without fast, because to show basically the contrast between inference and training. And so you can see fast accum does have some tangible impact. And also the results here in general are just are better than what we got for just the ReLU add. We have generally an 8% speed up geomean. These are also on the llama shapes, by the way. And you can see with CUTLASS without fast accum that we get a 16% speed up over Triton. And then the max speed ups are also pretty significant. The reason the FP-GEMM speed up is so high is I think there were some heuristics where FP-GEMM was weirdly slow on some of the shapes we ran. So I just take that with a grain of salt. I don't know if that's CUTLASS being really good or FP-GEMM not doing so well on some shapes. And then 3332 is the instantiation level. I kind of alluded to this earlier, where some libraries will have a user tunable level that allow you to tweak the search space. And so we picked this instantiation level because this was the largest search space that if we went larger, it didn't seem to give a lot of extra performance benefit. And so once again, here's a chart of the FP8 performance results. CUTLASS does really well across all of the llama shapes again. And we also range from m equals 64 on the left to m equals 65,000 on the right. On the left, with small m, CUTLASS seems to dominate the other backends. But on the right, it gets a little more muddled, where Triton does well as well. And so now I'll switch gears to CuteDSL, which is the new DSL that Nvidia is releasing to in essence, eventually be the new language everybody will use for auto-tuning. And so this language is easier to maintain because it's implemented in Python. And the main benefit is that it has faster compile time, like 100x. And the reason that's the case is it uses a custom MLIR compiler versus NVCC to generate PTX directly from the Python code. And there's been a lot of OSS adoption. TreeDAO, Flex Attention, and both Flash Attention have adopted this. And it uses the same abstractions as CUTLASS, so in theory, it should be able to get the same performance at the PTX level. And similarly to CUTLASS, we take the approach of implementing templates in TorchInductor for CuteDSL. These templates are a lot simpler to maintain since they're implemented in Python. They're faster to compile, as I mentioned, and the one drawback is, although since CuteDSL is pretty low level, it can be very verbose. Some of the GEMM implementations can be thousands of lines of code. But overall, the performance has been quite good, and I think justifies this investment. And so here's some early performance results with CuteDSL. We show the Flex Attention version with Triton versus the Flex Attention implemented with Flash v4, which uses CuteDSL. And this really illustrates that the Triton performance really has not been the best on Blackwell. On all of the different Flash Attention shapes here, we're getting over 2x performance improvement over Triton. And so in the future, I think this really justifies our investment. We'll continue working to get CuteDSL to implement more operations. And that's everything we have, so any questions? Oh, yeah.
So you said that for the autotune, correct me if I'm wrong, but like you said that it can just stay against inference one shape, but the
Testing. Okay. Yeah. So it's not very fancy. It's just the kernel would take in tensor pointers and then some metadata, which is like the shapes and the stride. And then because when we compiled the CUTLASS code, we didn't make them static, so they didn't get hard coded in the CUTLASS kernel, so they can just handle most of the shapes, most of the dynamic shapes. There are some small constraints with which dimension it could be dynamic, which dimension couldn't be dynamic. There are also some concerns with layouts, but for the most part, it's pretty dynamic.
In that same vein, CK is mostly a templated library, so a lot of that has to be kind of already baked in at compile time. So how do you handle the specialization of CK being good on various types of shapes when a lot of times the gems themselves need to be hard-coded for very specific tiling template parameters?
I don't.
Well, the question is the question that how do we specialize at compile time on things that can change at runtime, or? Yeah, sure. I mean, more interested in how at runtime we're going to, auto-tune pretty specific gems when, for something like CK, which is something that I'll work with a little bit more closely, a lot of that has to be decided at build time because it's a template library. Oh, okay. So since we're a JIT compiler, we actually run the static build of the CK kernels at runtime. So we get basically the shapes from the workload, and then we run their whole compile pipeline at runtime. And then we guard against if the shapes change. Oh, well, if we have dynamic shapes, we'll basically reuse those same kernels no matter if the shape changes, and you'll just have tuned on one specific set of shapes. If you're not using dynamic shapes, we'll recompile if there's a new a shape encountered, so we guard on the shape. Compile for the first time you encounter a specific type of shape? Yes. And then if, yeah. What is the overhead for that compilation versus non-compile? So, did you want to jump into that? Or?
What about overhead for compile, not compile?
For instance, in JIT, you compile that first time because you just encountered a new shape. Now, let's say the next time you run the same shape, you don't need to compile. What's the overhead between the time you had to compile and the time you didn't have to compile?
It's not that bad because we compile them in parallel. Eyeballing, I think CK per kernel is like a few seconds per compilation, but you do it in parallel. It's not that bad. CUTLASS is the one that is taking more time. So happy to follow up more, but then I think we're running out of time.
Thank you, everybody.
Thank you.